Okay, let's begin our study of capacitors. What is a capacitor? Well, fundamentally, the capacitor as a circuit element is simply formed from two parallel conductors with a dielectric or an insulator between those conductors. So that's ultimately, fundamentally, all that a capacitor is. It's formed from two parallel conductors. There are a lot of different types of structures that you can build and make a capacitor. But we're just going to look at one of the simplest ones. In this case, what we call a parallel plate capacitor. And in this case, what I have here is I have two rectangles of some conducting material, usually metal of some type. So I have conducting plates. I also have some dielectric between those two plates, some sort of insulating material. And this dielectric can be glass, plastic, it can be air, or it can be vacuum. In other words, anything that something that separates those plates that keeps current from flowing from one plate to the next. Now, the way a capacitor works is we're going to store energy in the electric field that is formed in that dielectric. Now, in addition, I'm also drawing two terminals. We have to connect something to the capacitor. So I will have two terminal wires, one attached to each of the two conducting plates. So in its simplest form, that is the structure of a capacitor. Now, capacitors exhibit a property called capacitance. And capacitance is simply nothing more than the measure of the capacitor's ability to store electric energy, or to store energy in the electric field. So in this case, we've got a parallel plate capacitor. Let's assume that the dielectric was just air, normal air. In that case, I could write an equation in terms of the geometry of this capacitor like so. So the capacitance for a parallel plate capacitor, and I want to emphasize this is for the parallel plate. Different structures will have different equations that describe the capacitance. But in this case, for the parallel plate capacitor, C is equal to epsilon times A divided by D, where C is the capacitance in units of farads. Or we just abbreviate that with a capital F. So for this capacitor, C is equal to epsilon. Epsilon is the electric permittivity of the dielectric. And in the case of air, this would be equal to 8.854 picofarads per meter for air. Different materials, different dielectrics will have different permittivities. In fact, that is a very active area of research in integrated circuit design, where people want to try to find improved dielectrics for capacitors in order to increase the capacitance as much as possible within the smallest amount of area. So if you're into material science or semiconductor physics, you'll possibly wind up working for some company involved in semiconductor manufacturing and actually investigating dielectric materials. Okay, now in addition, what is A? A is the area of each of the parallel plates. So in this case, each of these plates has an area of A. And finally, D is the width of the dielectric, or the spacing between the plates. So how thick is our dielectric? What's the thickness? And in that case, D is going to be this dimension, the thickness of that dielectric. Okay? So, here's our basic equation. And once again, as I mentioned before, epsilon is going to be a function of the material. Different materials will have different dielectrics, and in fact, trying to find capacitors with larger dielectric, or actually finding dielectrics with a larger value of electric permittivity is definitely something people care about. Okay? Now, something to emphasize. Capacitance exists between any two conductors. So anytime I have two conductors that are not in direct contact with each other, there's a capacitance between them. I can take two pennies and sit them on a table, two tables at opposite ends of a room, and there will be a very, very small but measurable capacitance between those two pennies. So everywhere you look, there is capacitance. Capacitance is basically one of the, one of the properties of the universe, just as resistance is, that you see everywhere in all substances. All right? In fact, this leads to an issue where in more advanced circuit design, you have to deal with what are called stray or unwanted capacitances. And you'll sometimes also hear those called parasitic. And generally these are capacitances we don't want. Now, in general, in this course, we're just going to be dealing with capacitors as a lumped unit. We're not going to deal with issues such as parasitic or straight capacitances, but if you take, for example, more advanced courses in electronics, then you find out that this really isn't something you can ignore. It actually becomes very, very important to the behavior of the circuit. So I just want you to be aware of it, although it's not something we're really going to deal with in this particular class. All right? Something else to mention too is the unit of capacitance is the farad, but a 1 farad capacitor is very, very large. That's actually a very, very big capacitor. Typically in circuit design, the range of capacitor values you'll normally see will tend to be more on the order of picofarads, 10 to the minus 12th, to microfarads, 10 to the minus 6th. That's really a more common range of values you'll see in an electronic circuit. Now you can actually find very, very large capacitors. They're called supercaps. And you will actually see this used in electronics. These basically act as energy storage devices to hold a lot of energy. So for example, if you've got a battery-operated piece of equipment and the battery is dead and you need to swap it out, you can pull the battery out and the supercap will keep the circuit working, keep the memory intact until you can put in the new battery. So you will see supercaps, but you don't normally see them in basically standard or modern electronic devices, certainly not in integrated circuits. All right? So what is the schematic symbol of a capacitor? Let's go ahead and let's do that. This, of course, is kind of a physical representation. How do we actually draw it and put it into a circuit schematic? Well, the schematic symbol for a capacitor looks very much like that representation of the parallel plate capacitor. It's kind of an idealized representation. So I've got two parallel plates with two terminals. And that's my capacitance C. And of course, as with every other electronic element, every circuit element, you can always draw this in any orientation you want. You can draw it horizontally, vertically, diagonally, it doesn't matter. And you can represent the voltage and the current. Once again, I and V. There's going to be a current and a voltage associated with it. And once again, we note these are defined according to the passive sign convention, just like the resistor. I, in fact, the current will be equal to I is equal to C dV dt. And here's where we see where the calculus comes in. The current's equal to the capacitance times the time derivative of voltage. So I is equal to C dV dt, where I and V are defined by the passive sign convention. So just as with the resistor, the capacitor, you have to use the passive sign convention when relating voltage to current. All right? Now, there's an alternative representation for capacitors. In some schematics, you will see this. Where one of the plates will be curved. When you see this type of schematic representation, what that represents is what is called a polarized capacitance, where the curved plate is the negative plate. Now, some capacitors, it doesn't matter which plate is negative and which is positive. It works equally well both ways. Other capacitor structures, for example, electrolytic capacitors, which you would see in your next circuits course or an electronics course, they are polarized. You can only put a voltage of one polarity, of a certain polarity across them. And in that case, you may see this curved plate to indicate that that is the negative one. So in this case, as far as we're concerned, there's going to be nothing fundamentally different between this and this beyond that curved plate. And in general, in the current textbook we use, it normally just goes with this more conventional representation. Okay? Now, we note from this equation if dV dt is equal to 0, in other words, if the voltage is constant, in other words, if the voltage doesn't change with respect to time, then I is equal to 0. The current flowing through the capacitor is equal to 0. In addition, I can flip this around. I can take this. I can say, if I is equal to C dV dt, I can rewrite this and say I dt is equal to C dV, and I can now integrate both sides. The integral of current is charge, which will be equal to capacitance times the integral of dV, which is voltage, which means Q is equal to CV. In other words, the charge that is stored on a capacitor is equal to the capacitance times the voltage across the capacitor. So this is one of the other fundamental equations to do with capacitors, and this comes right out of I is equal to C dV dt. All right, now, when looking at capacitors, inevitably, some students will look at this and they'll realize there's something wrong, something that we're being told that seems to contradict something we were told earlier. And let's consider this for a moment. Perhaps you've already recognized what that is. Here I have with a capacitor, this is an insulator in the dielectric. And yet clearly I'm indicating a current flowing into that capacitor and flowing out of the capacitor according to the passive sign convention. And that seems to be contradictory because we've already said currents cannot flow through insulators, right? You need a conductive path. So this seems a little bit contradictory in terms of the behavior of the capacitor, the fact that we're talking about a non-zero current. Well, just want to make this clear that the kind of current that flows through a capacitor is not what we have talked about before. It is not what we call a conduction current. So a conduction current doesn't flow through a capacitor, and that's what we've been thinking about before when we talked about current. It was a conduction current, a current that had to flow through a conductor. Instead, a capacitor has a displacement current. And this displacement current is a function of charge movement in the dielectric. Now, I'm not going to bother to go through all of the physics of that, but you can kind of just, for now, take it as a given that it's actually two very different physical mechanisms. But here's the nice thing. Even though what flows through a capacitor is not a conduction current, as far as circuit laws are concerned, KCL, KVL, we can treat it exactly the same. So for analysis purposes, we can treat both types of currents exactly the same way. So when we're going through and we are using the passive sign convention or we're using KCL, doesn't matter what type of current it is, whether it's a conduction or displacement current, we can treat it the same way, which is a good thing, which means that everything we've learned so far we can still apply in terms of circuit analysis. Okay, now let's take this a little bit further. Let's look at this equation, I is equal to C to V dt. I'm going to rewrite this. I'm going to rewrite this as IT is equal to C dVt dt. In other words, what I'm indicating here is both the current and the voltage are going to be a function of time. All right? So in this case, I'm going to write this such that IT dt is equal to C dVt, and I just brought the dt over to the other side. And what I'm going to do here is I'm now going to go through and do a little bit of integration with this. So just to simplify this, I'm going to just say this dVt. I'm just going to call that dV just to make it easier. And in this case, I'm going to say, therefore, that dV is equal to 1 over C IT dt. So just rearranged terms and brought everything over here in terms of dV. And now I'm going to integrate. I'm going to take this, and I'm going to integrate both sides. The dV, I'm going to go and write this as Vt0 to Vt as the limits of dx is equal to the integral of t naught to t, the limits, times 1 over c times I tau d tau. So what I've done here is I'm simply integrating between some limits for both the voltage and time. And notice x and tau are my variables of integration. And so from here, I can now go ahead and evaluate this integral. So in this case, if I evaluate this, I'm just going to get Vt minus Vt naught for my limits on the left side of the equation. On the right side, I'm going to get, that's equal to, well, the capacitance value I can treat as a constant. I can bring that outside of the brackets. So that becomes 1 over c, integral from t naught to t of I tau d tau. And therefore, I can now bring this term over to this side, and I have that v of t is equal to 1 over c, integral t naught to t of I tau d tau plus Vt naught. And what I've just done here is I've just derived the equation for voltage in terms of current. So over here, I was equal to C to V dt. Over on this side, V is equal to 1 over C times the integral of I, plus this term. And what is this? That term is the initial condition of the voltage across the capacitor at time t equals 0. So at time t equal t0, the voltage across the capacitor is my initial condition. And we will see this concept of the initial condition in both capacitors and inductors. So this is nothing more than this equation rewritten in terms of voltage. Instead of current in terms of voltage, voltage in terms of current. So notice once again, I've got differentiation here, I've got integration here. As we're going to see later on, that has a lot of very important consequences. The fact that, in effect, there is this relationship in terms of calculus between voltage and current. Okay? Now, given these two definitions, I can now write a couple of other equations to go with that. Let's consider the power in a capacitor. Okay, for any circuit element, P is equal to V times I, for any element. It's true now, it will be true to the end of the semester. It was true from the very beginning. And in fact, I can write this a little more exactly by saying the power at any time t must be equal to the voltage at some time t times the current at some time t. So this is going to be true for a capacitor, which means I can now take this equation and I can substitute in one of these two expressions into that equation. And therefore, P is either equal to C times V dV dt. So in other words, I go here and I say that I is equal to C dV dt, and if I substitute that, I get this. I can also say that if I substitute the other term, that P is equal to I times 1 over C integral from T naught to T times I tau d tau plus Vt naught. So if I substitute to get rid of current, I get this. If I substitute for the voltage, I get this. But what I have here is an expression for power. And power can change with time in a capacitor depending upon the value of the voltage and the current, which also tend to be time-varying quantities. All right? Now, we note, depending upon whether or not the voltage or the derivative voltage have the same or opposite signs, we note that power can be positive or negative. So depending upon, and both the voltage and the change of time with voltage can have different signs, or the same sign. And what that means is power in a capacitor could be positive or negative. So power may be greater than 0. In other words, it's absorbing power. or I should say more accurately, it's absorbing energy. It has positive power, it's absorbing energy. But when we're absorbing energy, that doesn't mean we're dissipating. This is not dissipation. Not like a resistor. It's not giving off that energy as it absorbs it. It's not radiating it as heat or as light. Instead, it is storing it. And that's a fundamental difference between a resistor and a capacitor. Or power can be less than zero, in which case it is releasing energy back into the circuit. So in this class, we're always going to be assuming that capacitors as ideal elements never dissipate any power. So we're always going to have them they're always going to be storing energy or releasing energy, but other than that, they are ideal devices, unlike resistors, which always dissipate power. Okay? So as well as power, we can also talk about energy. Power is the derivative of energy with respect to time. Once again, that's one of the fundamental equations we first looked at the beginning of this class. So looking at this, I can also say that it's equal to CV dV dt. In other words, power is C times V dV dt, therefore that must be equal to the change in energy with respect to the change in time. And so therefore, I can take this equation, I can multiply through by dt, and I can rewrite this and say that dW is equal to C times V dV. Once again, I can go through and I can integrate both sides of that equation. The integral of dW is just going to be equal to W, energy. And in this case, I factor out the C. The integral of V dV, the integral of V is going to be V squared over 2. So pretty basic calculus. Therefore, this is equal to 1/2 times CV squared. In other words, this is the energy that's stored in the capacitor. And of course, this is in joules, just like all energy. It's equal to 1/2 times C, the capacitance, times V squared, where of course V is the voltage across the capacitor. Okay, so that covers all the basic equations for how a capacitor behaves in terms of the relationship between voltage, current, and also power and energy in a capacitor. So next time we'll look at a simple example of a capacitor and see how we can apply these equations. And at the same time, we'll talk about some of the kind of fundamental properties of a capacitor you want to keep in mind as you start doing more circuit analysis with them.